The partial molar quantities that we've learned about now may seem to be a little bit unusual, but they have special properties that will really come in handy. And one of these has to do with the fact that they are homogeneous functions. So let me talk a little bit in this video about the mathematical properties of homogeneous functions so you can understand what that special property is, and then we'll be able to apply it to learn something really neat about these partial molar quantities. All right, a homogeneous function. Let's suppose I have a multivariable function, f, and it depends on several variables, x1, x2, and so forth. I won't number them because it could be any number of variables. All right, now this is a function that if I multiply all of these variables by the same constant, so in other words, if I multiply each of these ones by a constant a, if I should find that in fact this is just equal to a raised to the n power of the original function, then this is a homogeneous function and it has of order n. All right, now this may seem really bizarre, and you may be wondering, how could a function ever have this property? What would be unusual about it? Well, as I mentioned, partial molar quantities are an example of this, and they have order 1. So they're, in some sense, particularly simple. But let me show you another example of a homogeneous function so you can get a real feel for what it is like. Let's suppose I have a cylinder, not drawn very well, but I have a cylinder, and it has a length of h and a radius of r. Okay, I know that the volume of that cylinder depends on both the radius and the length, and it would be given by pi r squared times h. Okay, now what if I were to scale both the radius and the height, the h, by the same quantity? So now I want to find out what is v of ar ah. Now, the first thing I'll note is that if we scale them both by the same quantity, we're not changing the proportions of the cylinder. We're keeping the cylinder basically in the same shape and form that it has. Okay, when we calculate its volume, it'll be pi times ar quantity squared times ah, and when we work all this out, it will be a cubed times pi r squared h. So we can see that this is just equal to the volume of the radius and height unscaled. And so now we can see that this, in fact, meets the criteria for a homogeneous function. So this volume of a cylinder is a homogeneous function of order 3. All right, now, so when this is the case, for a function, it has some other special properties that are worth noting. And in particular, what I want to do is I want to start with our initial definition of a homogeneous function and take the derivative with respect to that scaling parameter. So in other words, I want to evaluate the derivative with respect to a of this function in which I have scaled all of the variables by that same amount. All right, now how would I go about doing this if I were, say, doing a derivative like this for the cylindrical volume? Well, first of all, I would take the derivative with respect to each of these slots. Okay, so the derivative of f with respect to ax1, but then I need to take the derivative of ax1 with respect to a. Okay, this would end up doing part of that derivative with respect to a for the whole function. I would need to do this for each of these derivatives. Sorry, each of these variables. Okay, so really all I've done is the chain rule, but I've done the chain rule extended over many, many variables. Now, this is something that we'll soon identify as just the derivative of f with respect to this first variable. But this thing is very easy to evaluate because the derivative with respect to a of ax1 is just x1, and this is just x2. So we get actually a very neat and compact sort of relationship that this derivative that we're trying to evaluate can be written simply this way. And there are, of course, one term for each of the variables in the function. Now, since it's a homogeneous function, that means it also equals this. And in this case, the function doesn't have any dependence on a, only this prefactor that indicates the order of the homogeneous function. So d dA of the quantity a raised to the n of f of x1, x2, and so forth is just going to be n a to the n minus 1 times f of this, all these variables. So now these two things are equal to one another. All right, and let's now take one further step and look at what happens when we choose a scaling parameter of a is equal to 1. All right, so in other words, we didn't scale those things at all, but this relationship still has to be true, that these two things are equal to each other. So in this case, what I would have, and I'll put this in a different color just so we can highlight it a little bit, we would have n times a to the n minus 1, but that's just 1. So I'll put that in parentheses to indicate that we've accounted for it, times the function, and that's going to be equal to x1 times the derivative of the function, and now it's taken with respect to ax2, but that's just ax1, that's just x1, and the function, second variable times the derivative of the function with respect to that variable, and so forth. And you can see here that, I'll write the final result over here, that is just equal to n times the function. This is actually kind of a remarkable statement. This is something known as Euler's theorem. And it is, as I said, quite a remarkable statement. Even more remarkable if we're talking about a homogeneous function of order 1, because in that case, that means that this product of variables times the derivative of the function with respect to those variables added together is just equal to the function itself. And so that's what I'm contending is going to be true of these partial molar quantities. All right, let's see how it works in the case of the cylindrical volume. So when we do that, if we take the derivative with respect to A of the cylindrical volume, okay, this would be what Euler's theorem would suggest is that the derivative of the volume with respect to A would simply be r times the derivative of the volume with respect to r plus h times the derivative of the volume with respect to h, and that should equal n, the order, which is 3, times the original function. All right, is that going to be true? Well, the derivative of this function up here with respect to r is just equal to pi times 2r times h, or 2 pi r h. The derivative with respect to h is just pi r squared. So now when I plug these into this formula over here, I multiply this one by r, I'll get dv dA gives me 2 pi, r times this is going to be r squared times h. H times this other one is pi r squared h, and so it equals 3 pi r squared h, which indeed matches our expectation from Euler's theorem. So we can see how this works in practice. For a simple example like a cylindrical volume, it will work in practice also for the partial molar volumes, and that's something that we'll look at in the next video.